Hello and welcome to this video where I will be discussing my final year project, which is based around using deep learning in medical imaging, focusing on chest pneumonia detection. During the course of this video, I'll be talking about the aims and objectives of this project, what chest pneumonia is and what causes it. So what are the aims and objectives? Well, the aims and objectives of this project are to apply deep learning to the entire X-ray processing chain, from acquisition to image retrieval, from segmentation to disease prediction. Objectives include increasing productivity by reducing labor-intensive and repetitive tasks of analyzing medical images, also providing faster diagnosis and aiming to provide more accurate analysis than radiologists. Chest pneumonia is a type of chest infection that causes lung inflammation as a result of bacteria, viruses, and fungi. This results in the air sacs getting inflamed and filled with fluids, making it harder to breathe. Occurrence of pneumonia can be serious, so much so that it can lead to potential death. Bacteria, viruses, parasites, fungal, chemical exposures, physical damages to lungs, and other pollutions are all forms of microorganisms that can lead to the occurrence of pneumonia. X-ray images are often unclear. This can lead to considerable differences in the diagnosis of pneumonia amongst radiologists, therefore making the detection of pneumonia to be a challenging task. A convolutional neural network, also known as CNN, takes an input image of raw pixels, in this case a chest X-ray, and transforms it via convolutional layers, rectified linear unit layers, ReLU layers, and pooling layers. This is then fed into a final fully connected layer which assigns class scores or probabilities, classifying the input into the class with the highest probability. Applications dealing with image data such as image classification datasets, computer vision, or natural language processing make use of CNN architectures. First comes the input layer, which is the image of the chest X-ray. Next comes the convolutional layer, which extracts features from an input image. The convolutional layer preserves the relationship between the pixels by learning image features using small squares of input data. Next comes the ReLU layer, which is an activation function that sets negative input values to 0. This simplifies and accelerates the calculations and training. Next comes the pooling layer, which is responsible for reducing the spatial size of the convolutional feature. This is to decrease the computational power required to process the data through dimensionality reduction. Once the converted input image is in a suitable form, it gets flattened into a column vector. The flattened output is then fed to a feed-forward neural network. Over a series of epochs, the model is then able to distinguish between the dominating and certain low-level features in the images, stating whether or not if pneumonia is present. To showcase the results projected from the trained models, a graphical user interface is implemented using Python's tkinter library. The previously trained models were saved in a H5 file format, allowing their best weights to be loaded in order to make predictions. The interface allows the user to generate a report of the dataset, visualize the dataset, visualize image states before and after augmentation, and get predictions from either of the 4 trained models. Initially, the user is greeted with a welcome page where they are presented with 2 buttons, to begin or to exit. Upon clicking exit, the application closes. Upon clicking begin, the user is redirected to the second tab, which consists of all the menu options. Within the menu tab, the user is presented with labeled buttons for all actions. 2 for generating dataset report, 1 for generating the report and 1 for opening it. Next comes 3 buttons for visualization. Original outputs a sample of the images from the training set. Process outputs a sample of the training set with augmentation applied. Clicking on graphs will generate a bar chart representing the number of images in each set for the training, validation, and the testing. The user is also presented with 4 buttons in the model analysis section, each button representing a different model. Users can select the desired model which they want to use to make predictions. To generate a report of the dataset, the Generate button is selected. This generates a report that can be viewed by selecting the Open button, which displays the report in a TXT file format. This generated TXT file format contains several pieces of key information about the dataset, such as the title, the source when it was last updated, description, and the number of images in the validation set, the training set, and the test set. The state of the images before augmentation is applied can also be viewed by selecting the original button, which generates a 3x3 sample of the images in the training set before augmentation is applied. As seen from the generated sample, we can see that obviously these images are in their original state and their dimensions also differ from one another, which is something that will need to be addressed in the augmentation stage. The state of the images after augmentation is applied can also be viewed by selecting the Process button, which also generates a 3x3 sample of the images in the training set after augmentation is applied. As seen from the outputted sample, we can see that obviously at this stage the augmentation has been applied. Rescaling has been applied with all the images now being the same dimension. Other types of augmentations have also been applied, such as shear range, zoom range, fill mode, horizontal flips, and vertical flips. Selecting the Graphs button outputs 3 graphs, which are generated to provide the visual representation of the number of images in the training, validation, and test sets of the chosen dataset. The first graph illustrates the number of images in the normal and Pneumonia states present in the training set. The second graph illustrates the number of images in the normal and Pneumonia states present in the test set. And finally, the final graph illustrates the number of images in the normal and Pneumonia states present in the validation set. The model analysis section contains 4 trained models which can be used to make predictions. This includes the VGG16 model, the VGG19 model, the ResNet50 model, and the MobileNet V2 model. Upon selecting the desired model, a summary of its architecture is printed, along with a summary of the model's architecture after the fully connected layer is also being applied. Then after, the model will start making predictions given the H5 file which the model was previously trained on. Prediction times will vary from model to model. Models with deeper architectures will naturally take longer to make predictions than ones which don't. Once the model has made its predictions, its results are outputted. Firstly, the model outputs what it predicted in a float form. This float is then converted into a binary form which when above the threshold of 0.4 is set to 1 and when below is set to 0. This allows a binary form of the prediction to be compared to the actual label of the image. Based on the binary predictions and the actual label, several metrics are measured, such as confusion metrics, testing accuracy, testing F1 score, testing precision, testing recall, and prediction time, which all provide insight on how the model has performed. The outputted metric can then be used to draw a comparison between the models.